Hello everyone, welcome to another talk in our webinar series. This webinar is also being streamed live on YouTube. You can find the link on our website or access it on our YouTube channel. Today we have Petar Zecevic from SV Group and the University of Zagreb talking about using AXS for large-scale astronomical analysis. Petar, thank you very much for coming.
Thank you for inviting me, Michelle. Okay, can I start?
Yes, please go ahead.
Okay. So thanks everybody for joining. As Michelle, I hope I pronounced it right. As he said, I'm going to talk about AXS. This is a system we built. I built with colleagues from University of Washington for large-scale astronomical analysis. So I'm going to show you a bit of the details of how we built it and why it's so fast with cross-matching, and I'll also show a short live demo. So I'm CTO at SV Group Zagreb, Croatia. That's a company of about 40-something people here in Zagreb. I'm also a PhD student at University of Zagreb. That's a computer science student. I'm not an astronomer, just to be clear about that. And I'm also visiting fellow at Direct Institute at University of Washington, meaning that I'm collaborating with them. And I also wrote this book, Spark in Action, which came out a century ago, seems to me, back in 2016. So it's kind of outdated today. There's second edition now out. Well, the story for me mostly begins with the LSST project, formerly known as LSST, which is today called Vera Rubin Observatory. And LSST used to stand for Large Synoptic Survey Telescope. Today that's been renamed to Legacy Synoptic Survey Telescope. And the people from Department of Astronomy at University of Washington, they play a big role in the project. They're deeply involved with data processing and, well, actually with mirror production and so on, at all levels of the project. What makes LSST so unique is that it's both wide and deep, so it captures a big area of the sky. And it also goes deep, meaning that it can capture many details and with large resolution, capture the faintest galaxies. It has or will have the largest camera in the world. Just the other day, a news came out that this camera was successfully tested. So I'm guessing they will transport it soon to the Paco Theron, I think it's called, the hill in Chile. The mirrors are already there. And LSST will spend 10 years continuously observing the night sky and produce the first video of the universe, because it will observe each object in the sky by an average of 700 times. So you would get 700 frames in this video, which will be pretty cool and provide an unprecedented amount of data, scientifically useful data. And it will probably start in 2023. It is stalled again a bit because of Corona things. Well, I hope it will pick up speed again. So the LSST's goals are: what are dark matter and energy, to answer those questions, to make a catalog of solar system objects, potentially including dangerous asteroids, then to track transients. I'm guessing most of you are astronomers, so you probably know that transients are all those changes in the sky, things that change between two observations. For example, supernova exploding, or meteor or asteroid moving, comet moving, one moment to the next. And within 60 seconds from detecting such change, it will produce an alert and send this alert to worldwide scientific community, those subscribe to such alerts. And it will also study structure and formation of the Milky Way, although there are better projects for that, probably Gaia or others. In numbers, it will have about 7 trillion detections of objects, light sources, which would make about 37 billion unique objects, stars and galaxies, asteroids, with nightly alert rate of about 10 million, nightly data rate 15 terabytes, and in total it's expected to produce about 83 petabytes of data. These numbers are not so huge in today's high-tech world. Some big companies are producing such amounts of data already. However, for an astronomical project, it is significant, and it's still challenging to process all the data and usefully analyze it and produce some science. And it's all stored in a queryable catalog. So again, I'm guessing that you all know that astronomical catalogs are just databases that where each row corresponds to a detection or an object. So we have each row contains measurements for observed star, galaxy, asteroid. However, getting those catalogs, databases, and measurements from images is not trivial, and mostly it's done by so-called data processing pipelines, which can be more or less complicated depending on the size of the project. So first, when you get an image from a telescope, you need to estimate the background. You need to estimate PSF, point spread function, which determines how the point light source spreads on the focal plane of the telescope on the image you get. You would get some kind of blurry image, which should be actually just one single point. And that's crucial. PSF estimation is crucial and not really simple, and depends on background, and background depends on PSF, and so it's done in iterations. You need to detect objects, you need to co-add images to improve signal to noise ratio. You need to do deblending if there's crowded fields where there are many bright objects next to each other. You need to separate them somehow. That's called deblending. So all of that can be really challenging and can involve lots of complex statistics and so on. But once you have it, then astronomers typically, I wonder if you also follow something similar, but they typically use some kind of interface to query or subset the data from such a database using something similar to SQL. For example, SDSS has a public web SQL interface you can use to filter the data, and you can obtain a subset of this data, download it locally, and then do your science analysis, probably Python. I know that ESA, European Space Agency, uses mostly Java. From what I gather, in US, it's mostly Python. So it depends, but my sense is that it's mostly Python. However, this traditional approach doesn't really scale well. You cannot download the whole catalog. Things are huge, those databases. And LSST will provide a cloud service to using Jupyter notebooks and other tools. So to bring the code to the data, execute your analysis where the data resides on a large machine. However, still, it will not provide things that astronomers often need, which is combining multiple catalogs, cross-matching them, and working on the full data sets. If you want to do your analysis on a whole sky, and combining multiple catalogs, that still is not so easy. So that is why we built AXS, which stands for Astronomy Extensions for Spark. And it begins with people from Dirac Institute seeing the need for this next generation astronomical tool. And first thing that stands out with AXS is, and the thing with which we started, is to have efficient cross-matching so that you can cross-match catalogs on the fly, basically, so to speak. And it is based on industry standards on Apache Spark, which is important because you can get many things in industry are routinely used in big companies, and advanced machine learning, analytical things, and data processing functionalities are used and built often. You get that with Apache Spark for free, and you don't have to think about things like failover and distributing processing and so on. So that's all, you already have it in Spark. And it's also hundreds and hundreds of, if not thousands of developers are working on Spark, contributing to Spark. And the user base is just huge. And so there's quick bug resolution and development of new features. So that's great. And AXS also provides simple but powerful astronomical API extensions for Python. You can use it on premises or in the cloud. So the idea is to have those catalogs in S3 buckets, let's say Amazon Cloud, and you just spin up your own virtual machine, do your analysis, shut everything down, and that's it. So everybody can use the same catalogs and cross-match them the way they like. A bit of history of AXS was this system of a bit unfortunate name by Mario Juric called LSD. I think it's just a large-scale database. It is a tool for querying, cross-matching analysis of positionally or temporally indexed datasets. And it was a bit ahead of its time. It was inspired by Google's big table and MapReduce papers, just like Spark. And it solved the same problems, but in a specific way. It had fixed data partitioning, which introduced significant data skew. Then it's partitioning data by time. However, most queries do not slice by time, so that makes it slower in a majority of cases. It's not resilient to worker failures, something that Spark gives out of the box, and has a lot of custom solutions for things that are available in Spark also out of the box or elsewhere. And it's also based on older version of Python. So upgrading LSD would require much more work than developing something like AXS on top of Spark. So let's see what is this cross-matching function. I'm showing here a region of the sky with RA meaning right ascension, basically an X, and Y, which is called declination coordinate. And I'm showing two objects from two catalogs. The first one is are denoted by dots, and the second one are denoted by X's. And the dots have this search perimeter around them, shown as circles. You can also add some kind of similarity measure between the two objects on top of this spatial search. So Around each object from the first catalog, we are searching for objects from the second catalog, and we are showing a match with a gray circle if the object from the second catalog falls within this search perimeter. So if you have billions of objects in first and second catalog, this is not really a trivial thing. So we did this, we managed to make it very efficient by using cleverly partitioning data beforehand. So you have to partition data in a specific way based on zones. The zones algorithm made by late Jim Gray from Microsoft Research, who published lots of papers on Microsoft SQL database and astronomical applications. So we took his idea where you divide the sky into horizontal zones of certain height, and we adapted it for distributed architectures. We store data in Parquet files, which are bucketed by zone. And that means that when I say Parquet file, that's actually a set of files. I don't know, you probably know. Parquet is the most often used, I'd say, format in the big data world. And it actually, one single Parquet file consists of many physical files, which can be distributed on many machines potentially, or a single machine. But it's often, or maybe even exclusively, a set of files. So when you bucket it by zone, means that each of these physical files are called, in this case, buckets, and they contain all the objects that belong to a specific zone. Within those files, those buckets, we sort them by zone and array columns. That's X coordinate. Zone is a range. Zones contain ranges of Y declination coordinates, and array coordinates are X coordinates, right? And with one final detail that we designate a certain thin area at the bottom of each zone, a thin strip of each zone that we duplicate into the zone below. So a subset of the data is duplicated so that we don't have to, the processes do not have to look into the other zones or in the other physical files, physical buckets, and no data movement between workers is needed. That's why we duplicate data. I'll show you in a second. I think it will be clearer what I mean. So this is an example of partitioning the sky. Let's say that the whole sky is this big circle, and we partition it into 16 zones, and we have 4 buckets or 4 physical files. Then we sequentially put all the objects from each zone into corresponding bucket shown with different colors. And what's not shown is this strip, narrow strip or narrow border at the bottom of each zone, which data from which gets duplicated into the zone below. And when you start your, I'm not sure how familiar you are with Spark. I wanted to do a short introduction to Spark, by the way, but I decided against it because I don't think it would take a lot of time. It's not that easy to do in a few slides. So the way Spark works, it has several executors which can run on the same machine or on many machines. You could have thousands of executors distributed in a cluster consisting of tens, hundreds, or thousands of machines. Here, it doesn't matter how many machines these 4 executors shown run on. Let's say they are running on a single machine. So we have 4 executors, and we have 2 catalogs. And each of these 2 catalogs contains 4 buckets or 4 physical files. Then when we instruct Spark to join or cross-match those 2 catalogs, the way we made access, we made some changes in Spark so that each executor will look at only a single pair of the buckets, and without any need to look into the other zones or other bucket files. And so this can be done in parallel. In this case, you would have all 4 executors joining or cross-matching. It's their own pair of buckets in parallel. So you could cross-match the 2 catalogs, 4 buckets at a time in parallel, and so it consists of 4 buckets. So that's the whole data set is cross-matched. And what's important to say is that those 2 catalogs need to be bucketed in the same way, with the same number of buckets and the same number of zones. Otherwise, you can get incorrect results. Okay. So this shows the query plan from Spark SQL's page of its web console, where you can see that there is no Spark generates those these blue boxes are like stages in the execution plan. And if you would have an exchange, a blue box called exchange, that would mean that some data movement between partitions needs to take place. And that's super expensive operation, especially if you have billions of objects. Then all of the data needs to be shuffled around the cluster and put in the correct machine, correct executor. So that would be a big no-no in when you're writing Spark applications. So here we managed to do this without any shuffles, without those exchange steps. And what this image basically tells you is that Spark will just read the 2 files in parallel and then directly do the sort merge join without any data movement between partitions. So that's great. And that happens because we introduced this change in Spark by this Jira ticket with this ID. Unfortunately, it hasn't been included into the main Spark distribution yet. But actually, it contains a version of what's called an epsilon join. So in case when you have data in bucketed, as I explained, and when you issue a query with conditions such as these, where you have a first column that you are joining on, that's an equi-join, where zone from the first table is equal to the zone from the second table. It's called an equi-join. And then you have an additional range condition based on a second column. In that case, we introduced this feature where we have a moving window going over the rows of the second table within the zones, and keeping in memory only those rows that fall within the condition specified within this range. And that way, Spark needs to go through the data set only once, and it needs to keep in memory only the minimum amount of number of rows. So that's pretty fast. And I'll show you first the some performance results. We've done those tests on a single machine. And for example, Gaia with 1.7 billion rows, when we cross-match it with ZTF, which contains about 3 billion rows, we can do it in 40 seconds with warm cache and about 5 minutes with cold cache. Meaning that the cache is the file system cache. So when Linux is reading things from files, it caches them in memory if it has any memory available for that purpose. And cold means that nothing is cached. The cache was clear before we ran it, so all the data needed to be fetched from the files. And warm cache means that data was partially cached. It's hard to say how much exactly, but we are certain that not all of the data could be loaded into memory. So maybe 30–40%. Other approaches to the sky partitioning are what's typically used is hill picks or HTM partitioning schemes, and those are great if you want to have a really highly granular way of partitioning the sky or Earth, and and if you want to describe some different shapes, for example, some complex regions of the sky or Earth, you can use Hillpix or HTM for doing that. However, for cross-matching, it's not so efficient, and it should be much slower than the zones algorithm. So this is an example of the API. I will show you a live demo, so no point in going through this. So we have cross-matching region queries, cone queries, cone being where you provide a point and the radius, and you get all the objects falling within that radius. Histogram and 2D histogram. You can use for handling light curve data. Light curves are when you have an object, for example, a star, and you observe it 200 times, you get 200 measurements. So that would be light curve data. And you can store that in an array, and Spark provides array functions. So you can do and analyze the data using Spark's array functions. And of course, you have all the other Spark functions, such as machine learning modules and graph algorithms, and what else? SQL and so on. So today, AXS is heavily used inside Dirac Institute. It's also evaluated use at several other universities, I think in Chile, in Europe, several places in US. And it is currently ran on Kubernetes on demand with catalogs in S3 buckets. That's how people from Dirac Institute use it. And we hope it will empower new astronomical discoveries in this century. So now it's demo time, hopefully a bit more successful than SpaceX launch. Let me unshare the screen. I think I have to. Oops, where is it? Just a second. Let me find the. Is it this one? Okay, here it is. All right. So a short demo. We need to. I'm already connected to. When I was preparing the talk, I already connected to the Spark cluster. I have a Spark cluster on a machine with 28 executors. Driver has 4 gigs of memory and executors 8 gigs of memory. And I also connected to the Spark web console. So you can see that I've already ran some jobs here. You can see how the executors on the executors tab. So that's 29 active processes, including the driver. And you can see, some statistics here and how much data you've read and written and so on. You can examine the, this is all part of standard Spark out of the box. You can examine the environments that are environment variables that are set on in your environment. And you can also see the SQLs that I've ran. So I don't know, that's where I got that screen I've shown you previously. So this shows you the plan, how Spark planned to execute some query that you said you want executed. So that's
So just a question. I mean, is this plan is this plan constructed on the fly? Is that it? I mean, you make a query.
Yes.
And, okay.
Yes.
Okay.
Yeah. Okay. So the first thing when using AXS, you connect to your Spark cluster, which can be a local cluster, it can be a distributed cluster. There are many variants. You can have a Kubernetes cluster, you can have Mesos, and you can have Spark standalone cluster. So I'm using Spark standalone here. And with just a single worker, if you're interested in that, that's minor detail. Then you use that Spark instance to create an instance of AXS catalog, which is your entry point to the to AXS. So here we can use the list tables function that gives us a list of tables available in the AXS meta store. So Spark has its own meta store of tables it knows about, and AXS has its own extra information on top of this Spark meta store. So AXS relies on Spark to Spark functionalities to physically load the data, but it also has a few other information extra about those tables, which is number of buckets I mentioned previously, zone height. This is 1 arc minute. This is the default. Which column was used for as the zone, for which column name is used for the zones, which column is used for array coordinate and declination coordinate. These two properties here are not currently used. So there's lots of tables here. This is the server on the Dirac Institute. You can also get just table names using list table names. So there's really lots of them. And you can also query the Spark catalog. So there's this confusion about catalog, right? So we have astronomical catalogs, which are big databases of observations. But in Spark terminology, that's a meta database containing metadata about the tables that Spark handles. So Spark has its own list tables command, and there you can get data, which database, Spark meta database this is, table type, description, so on. So there are also other, I will not execute this cell because this is dropping an example table. We can rename a table like this. This will rename the table in AXS and in Spark too. And if you have a table that sits on a disk somewhere, you know it's bucketed and sorted the way AXS wants it to be bucketed and sorted. You can use import existing table, say provide a name for the table and where to find the data, say how many buckets, what is the zone height, and whether to import it into Spark or not. If you say false, then that table should already be available in Spark. So if you want to, I don't know, reinitialize your AXS metadata but leave the Spark metadata intact, then you could use this, setting this property to false argument. And also, if you want to update, to change a bucketing information inside the Spark's meta database. So these are all details now. You do not need this information currently, but that's available. So now we want to load some of these tables that we listed there. We say load. I can execute this safely. So we have Gaia data from second release. We have Allwise data and ZTF. ZTF is the a project that LSST, parts of LSST's pipeline are tested on, and especially those alerts that I mentioned. And it's a successor to the PTF project. You can get table info for a single table like this, AXS catalog table info, or you can use the AXS frame instance. Each of these is an AXS frame. So I'll show you. So this is an AXS frame containing these columns of these types. And AXS frame is just a Spark frame with some extra properties and functions. So you can use AXS frames function to get the table info too. And what's important here, if we want to cross-match these three tables, we need to check that their number of buckets and zone height are the same. As I said previously, if they're not the same, you would get incorrect results. So we can do the count from the Gaia catalog. That would be what, 1.8 billion objects. Allwise, that's like 800 million. ZTF has 1.2 billion. We can look at the columns. So here, this property is comes from Spark's frame. This is not AXS feature, but the columns are the same. So we rely on Spark to provide this data. So this is also just plain Spark SQL. We can query the ZTF table like this for, say, where or filter, which is a synonym, and say the condition. So this is a Python way of constructing an SQL query. We can also write the query verbatim as SQL, and Spark supports ANSI, standard ANSI SQL mostly. So This query here will return all those rows that are duplicated. I mentioned that we are duplicating those rows from those narrow strips inside zones. So that's controlled with this by this column. And this is axis specific column, which is set to 1 for those rows that are duplicated, so that we don't cross-match them twice. And so what this gives you, if you've never used Spark, then that might be confusing at first. So if you execute this, you will get an axis frame and you will not get a result. So an axis frame or a Spark frame, they're just represent programs or plans how to do something with the data. And you wouldn't get the data until you execute a so-called action. So this was a transformation, giving you a different frame from an existing frame, transforming it to something else, and then you need to do an action such as count on this transform frame. So we can just count all the data that's duplicated. And now, because the data is indexed by, let's say, indexed by zone column and sorted by array column, Spark cannot skip any of the data. It needs to physically go into all 1.2 billion rows and check the value of dupe column in each of them. So that's why it takes a bit longer. Okay, so we have 170 million duplicated objects out of 1.2 billion. We can see how many zones we have by selecting the zone column, which is also axis specific column, and calling distinct. This is also a transformation, so we get a new axis frame, and then we need to call count. This should be quicker because okay, so we have almost 7,000 zones, which is the default. So now we can also do, for example, this is also standard Spark SQL stuff, nothing axis specific yet, except for those columns. So here I'm grouping the data by zone, counting within those groups. So this gives me 2 columns, zone and count. And then I'm ordering by count and then calling show. Show will format the output like this. Shouldn't take too long, I think. Okay, so we can see that the zones are skewed, and which is to be expected because the sky is very skewed. There you have Milky Way and you have parts of the sky with very rarely populated. So we can see exactly how, for example, the average count of objects in each zone, maximum count and minimum count, doing something like this. We have to import Spark functions and then call those on the grouped by object. So the zones are skewed. However, that doesn't mean that the data is skewed on disk, because zones are put sequentially into buckets, if you remember. And because zones are rather thin, that means that the sky is finely, like, there are like stripes, horizontal stripes that are sequentially put into each bucket, and that like shuffles the objects around the buckets, let's say, and you get pretty even out counts or the bucket sizes are pretty even. Okay, so that was a bit of plain Spark SQL. So this is specific to AXS. So this will query the region between point 4045 and 4146 degrees RA declination. And we will just count number of objects within that region of the sky. And this is the same as doing this query. RA is between 40 and 41, and DEC is between 45 and 46, except that AXS also does some special additional query if the RA range spans the prime meridian, and also it will add a condition on zones, because the DEC declination range corresponds to a certain range of zones. So if you first constrain the query to look only at some of the buckets by specifying zones, then you can speed things up. And we can see this Gaia data that we have in this region using show. There's lots of columns, so it's not really readable. So we can just select a subset of the columns and show the first 3 rows, for example, like this. Okay, so for cross-matching, we can say cross-match Gaia with ZTF and use the search radius of 3 arc seconds. This will give us a new frame. And now we can do the count. So last time I did this, it was almost 2 minutes. So I'll save us some time. I won't execute it now. And it gives us 800 million results. We can also save this result as a new AXS table, which means that it will be partitioned, bucketed, and sorted the way AXS wants it to be sorted, just like using this command. But this would involve moving lots of data to a new place, so I will not execute this. We can also, for example, cross-match 3 tables, all-wise, not unwise catalog. So it's, however, some of the tables have the same names. So this little snippet will find the tables that are the columns that have the same names in those catalogs. As I said, DEC, dupe, RA, and zone are AXS specific, and those aren't important. If they are the same, it's okay. They should be the same. But designation, PMDEC, PMRA, source ID, those are the same in 2 or more tables in those. So in that case, if you join tables like this, you would get a single output table containing data from only one of those input tables, and that's probably not what you want. So in that case, you would do something like this. Before cross-matching them, you would rename a column into something else. So I'm renaming only one of those just to show you how to do it, what might be a problem. So now the cross-matched AXS frame, we can also use this print schema. I don't think I've used it before. Print schema will show you the types and names of all the columns, and also if they are nullable or not. And this cross-matched table now contains the columns from all the joined tables, right? So this cross-match also will take about 2 minutes to complete. Last time I did it. So I'll also save us some time here. Okay, so yeah, we can do a region query within this cross-match because it's just an access frame, so it has the region function available, and we can do the count. It took 3.66 seconds last time, so let's try. Yeah, so because we skipped many of the zones because of this rather narrow region, we skipped many of the zones, and Spark needed to look into just a small subset of the whole data set. Okay, so what else can we do? Okay, so ZTF has this magnitude with the G filter column, which is an array column. If you look at the schema here, the column has this definition: magnitude G, it's an array, and elements are floats. And so you can use Spark API to index into those arrays. So I'm just selecting the first element. So that would be the first observation for each object. And only in those rows where there are where this column is not empty, this array is not empty, or its size is greater than 0. So that gives us this first 20 rows look like this. And we can use Gaia's column containing G measurements also. And we can combine those two columns to create a histogram using AXS function for histogram. However, it uses integers to define those bins. So I will multiply this result by 100 to have some kind of number of bins. It took me 7 minutes the last time I did this. But what this does is looks at differences in G measurements with G filter in both catalogs, and then shows you a histogram of those differences. We can do a similar thing with a two-dimensional histogram by providing, sorry, I didn't say that 100 is the number of bins I wanted here. And in this case, I'm using two conditions for binning, one in x-axis and the other in the y-axis. And this is the number of bins for each one of those conditions. Last time it took 14 minutes because there's lots of data needs to be moved around a lot because you're grouping the data based on those bins and so on. But then you can use the result. This gives you X, Y, Z result, which can be used directly in the pcolorMesh function to produce something like this. Hopefully useful. And the final example is a piece of code I stole from a colleague, Colin, from the Iraq Institute, that uses HealPy's molview function, and to produce it uses Gaia dataset and creates a HealPix index with this granularity, and then it shows you this nice graph. So that's nice for ending the demo. Okay, so if there are any questions, I'd be happy to answer.
Okay, let me get started. Okay, Michelle.
Yes, go ahead.
All right. Oh, well, first of all, thank you very much. Extremely useful presentation. I mean, I know that we don't have much time. I just want to know, I mean, there is a lot of fine tuning that you can do, right? In terms of the number of zones that you define, depending on your disk space, memory. How
Yes.
you do that? I mean, how you optimize the scheme? Is there a cookbook or?
Well, it's a tricky thing. It's not easy, I know. I guess you've used Spark. Have you used Spark?
No, I haven't, but I've been reading about it. So, and
Yeah, well,
maybe I should buy your book, right?
yes, definitely. Although, as I said, it's outdated.
I'll wait for the next edition.
Second edition was written by Jean-Pierre. Oh, I can't remember the name now. Not me, actually.
Oh,
So,
I see. Okay.
but please buy his second edition.
All right.
Well, it's not easy to know in advance. It depends on your cluster. It depends on the machines you're using and on the data sets. And it's really difficult, and on the queries you're doing. So one query might turn out, great, and the second one might kill your machine. You can always do something really, that will use up all of the memory. For example, silly example, but you can just say collect, and that means that it will fetch all of the data from all of the executors, basically the whole data set, into the driver's memory. So that would obviously kill your program. There's no way. So you need to really be aware of the what's going on behind the scenes, right? And it looks simple. It's just SQL, and but it's actually distributed computations.
No, there's a lot of fine tuning required, but it's awesome. I mean, if this time that you're giving us, it's just extraordinary. Okay, great. Thank you.
Yeah, no, welcome.
All right, any other questions?
I'd like to make a question.
Go ahead.
Okay, thank you. Thank you, Petar. You mentioned before on your talk about spark arrays to store light curves. And then you said that there are some type of functions to analyze this type of data. Could you comment or give some examples on this type of functions for light curve?
Yeah, I don't have any demo with that, but there's a whole section on the Spark documentation about the array functions. However, probably you will, if you're doing something really smart with the light curves, I know there's this thing called the Lomb-Scargel algorithm or something like that. For example, I don't think that exists out of the box, or how to say, it's second dimension in the tables and rows, and you can do I don't know, indexing into those arrays. You can do counts, size, subset them, add elements into them, but doing some, I don't know, machine learning analysis on them probably would be easier if you would convert those values into rows, if you know what I mean. If you just explode the values of the arrays and turn them into rows, then it would be easier to distribute that computation, or you can always make your own a custom function using Arrow. Have you heard about Arrow?
No, I have not. But
No. So, well, that's another detail with Python and Spark. Arrow is actually a Apache project that aims to define how to serialize data across languages and systems. So you have it in C, Java, Python, and so on. And it tries to standardize how you serialize data so it can be manipulated directly in memory from both Java and Python. So it's not quite there yet. It's still slower to do it from Python than from Scala. So sometimes if you're doing it directly, manipulating those array data from Python, it could get slower. So I think it would be a good idea to first explode those arrays into rows and then use the standard Spark SQL functionalities, queries, functions to analyze that.
okay, all right. Thank you.
Okay.
All right, any more questions? So if there are no more questions, and seeing as we're a few minutes past the hour, I think we can wrap this up. You can find the video of this presentation on our website and also on LIneA's YouTube channel. Next week, we will have Keith Bechtold from University of Wisconsin-Madison to talk about Milky Way science updates from the US. Thank you, everyone, and a special thanks to Petar for a great presentation and a very helpful tutorial.
Thank you guys for the questions and for inviting me.
All right, thank you. Bye.
Okay, bye-bye.